In this video, we're going to continue looking at the arrangement of electrons in atoms, and specifically how we can display that arrangement so we can begin to see where each electron is. We talked earlier about the Pauli exclusion principle, which tells us that no more than 2 electrons can occupy the same orbital, in other words, only 2 electrons per orbital, and if we do have 2 electrons in one orbital, they must have opposite spins. This leads us to a general statement that no 2 electrons in an atom can have the same set of 4 quantum numbers. And for our quantum number overview, remember that the principal quantum number tells us what Bohr shell we're in, and that's quantum number n. We have the subshells within those Bohr shells, denoted by quantum number L. We have the orbitals within the specific subshells, quantum number m. And then within each individual orbital, we have electron spins, denoted by quantum number m sub s. When we're looking at the energy level of Bohr shells and orbitals, we have to take a look at an interesting effect that happens between the d sublevel of one Bohr shell and the s sublevel of the Bohr shell that comes after it. Because of an effect called screening, what happens is that the Bohr shell, the s sublevel in a Bohr shell, is actually lower energy than the d sublevel of the Bohr shell previous to it. In other words, a 4s orbital is lower in energy than a 3d orbital. What this means for us is that when we think of filling an atom with electrons, we would naturally fill the 1s orbital first. When the 1s orbital is full, we've filled up the first Bohr shell completely, so we'd move to the second Bohr shell, and we'd fill our s sublevel in there, and then our p sublevel. That would completely fill the second Bohr shell. We would then go on to the third Bohr shell and first fill sublevel s, and then fill sublevel p. But before we move on to sublevel d within the third Bohr shell, we would actually fill 4s. And then we would go on and fill 3d. And so this leads us to looking at the order in which electrons are added into an atom. And so we get a graphic that looks like this. And if we follow the arrows, we see that we first add electrons into 1s in our first Bohr shell. After 1s, we go to our second Bohr shell and we fill 2s. After 2s, we fill 2p. That fills our second Bohr shell. So we go on to our third Bohr shell and fill 3s. After 3s, we fill 3p. Before we move on to 3d, however, we fill 4s in the fourth Bohr shell. It's only after filling 4s that we'll come back around and put electrons into the 3d sublevel. After 3d, we then continue on in our fourth Bohr shell and fill 4p, and then 5s, and so on, and we follow this pathway. Then to 4d, to 5p, to 6s. We don't actually fill 4f until after 6s. And then 5d, 6p, and so on, until we finally fill Bohr shell 8. This is a fairly complex diagram to memorize. Another way that we can look at the order in which electrons are placed into an atom is by looking at the periodic table. We can see that we have some distinct blocks in the way that the table is set up. We have this block here, which we call the S block. We have the P block right here. then the D block, and finally, down below, what we refer to as the F block. And so the way that we can use this with what we call electron configurations and the order in which electrons fill an atom is to note that first 1s is filled. We're here in our first period. We fill 1s, then to helium now, we're still filling 1s. After 1s is filled, 2s is filled as we get larger and larger atoms. After 2s, we begin to fill 2p. After 2p, we fill 3s, and then 3p, and then after 3p, 4s. And we note that we have a break here as we get into our D subblock. Our number is one below the period number that we're in. So here we're in the fourth period, but for our D block, we're actually filling 3D. After 3D, we go on to 4P, and then so on, 5S and 4D, 5P, 6S. We do have to remember that we have a break right here in the table. At this point right here, we actually move down to our F block. And so after filling 6S, we move down and begin to fill 4F. And then we would come back up to 5D, 6P, 7S, 5F, and then finally 6D and 7P. Using this idea of blocks of the periodic table like this makes it easier for us to see and to remember the order in which electrons are added into an atom. And so you can either memorize 1s, 2s, 2p, 3s, 3p, 4s, 3d, and so on, or you can use the periodic table, which is a much easier method. Now let's take a look at how we're going to actually use this. We're going to put together what we call electron configurations, which begin to tell us exactly what Bohr shell and what type of orbital all electrons are located in within an atom. With electron configurations, we use a numbering system to indicate these electrons. We first provide the number indicated by the Bohr shell, 1, 2, 3, 4, etc. That number is then followed by the lowercase letter, which corresponds to a particular orbital. After that letter indicating sublevel, we have a number written as a superscript, which tells us the number of electrons within that orbital. For example, 1s2 indicates that we're talking about electrons in the first Bohr shell, in an s sublevel, and there are 2 electrons within that sublevel. This is not a mathematical exponent, so we do not say squared, but rather we say this as 1s2. And again, it means that we have 2 electrons within our 1s sublevel. And so let's take a look at how we go about these configurations. Let's say we're talking about a hydrogen atom, in which we only have 1 electron. The Aufbau principle tells us that we begin by adding electrons into the lowest energy orbital first. And so we're going to start by putting electrons into our first Bohr shell. We only have an s sublevel in that first Bohr shell, and we only have 1 electron for hydrogen. And so our electron configuration would simply read 1s1. Moving on to helium. Now we have 2 electrons. Again, we're going to start by filling our first Bohr shell. We have an s sublevel, but now we have a total of 2 electrons. So we have 1s2. For carbon, we have 6 electrons to worry about. So we're going to start, again, always, Aufbau principle tells us lowest energy first. So we're going to start in Bohr shell 1. We have an s sublevel. 2 electrons total fit into an s sublevel. And so now the S sublevel is full. The first Bohr shell is full since it only has an S sublevel. So now I have to move to the second Bohr shell. The second Bohr shell also has an S sublevel, which holds a maximum of 2 electrons. And so now I have to move to the 2p sublevel. Carbon has 6 electrons total, so I only need to put 2 more electrons in there. And so carbon's electron configuration is 1s2, 2s2, 2p2. Let's take a look at the configuration for aluminum. We have 13 electrons to worry about. We're going to start by filling Bohr shell 1. Then we move on to Bohr shell 2 in our S sublevel. We move to the P sublevel, which can fit a total of 6 electrons maximum. And so now we've completely filled up Bohr shell 2. So now we have to start putting electrons into Bohr shell 3. We'll start with our S sublevel. It can fit a total of 2 electrons. We're going to then move on to our P sublevel within Bohr shell 3. Aluminum holds a total of 13 electrons. We've already placed in 2, 4, 10, 12, so we only have 1 electron left, and so we get 3p1. And so this tells us when we're looking at all 13 electrons in an aluminum atom, 2 of those are in a 1s orbital, 2 are in 2s, 6 are in 2p, 2 are in 3s, and 1 electron is in a 3p. When we're looking at bigger and bigger elements, like iron and then even up to things like lead, there's an easier way to go about knowing where we end. Remember, we looked at the various blocks of the periodic table. We said that this is our S block, our P block, our D block, and our F block. And so what we can do is we can look at where an atom is located and know what its electron configuration must end with. And so let's take a look first at iron. So here we have iron in the periodic table. We see that iron is within our D block. It's within the 4th period. But remember that our D block has that feature where the actual Bohr shell there is going to be one below our period. And so in other words, when we're looking in this row here of the D block, we're actually filling 3D. And so this tells us that our configuration for iron must end in 3D. Not only that, it is 1, 2, 3, 4, 5, 6 spaces over in that D block, and so the configuration for iron must end with 3d6. Let's take a look at lead. So here's lead in the periodic table. Lead is 1, 2, 3, 4, 5, 6 periods down within the P block of the periodic table. And so we know that the configuration for lead must end with 6p, and it is 1, 2 spaces over within the P block. So the configuration for lead must end with 6p2. And so, when you're writing the configurations out for those elements, we know that iron has to end, we said, with. And so, when doing the configurations of these atoms, we know that iron must end with 3d6. So that means we can simply build the configuration up using the Aufbau principle until we get to 3d and put 6 electrons there, and we should be done. And so we start with 1s and its 2 electrons, move on to 2s2, 2p6, and now 2 is filled. We move to 3s2, 3p6. We know from there we fill 4s, and then we go back to 3d, And we said iron has to end with 6. And so, theoretically, this should be the electron configuration for iron. We can double check that now by adding all of our electrons up and making sure that they equal our number total of 26. 2, 4, 10, 12, 18, 20, 6 electrons. And so there's our electron configuration for iron. We said that lead has to end with 6p2. And so we can take a similar approach. We can simply start to write out our configuration using the Aufbau principle and just stop when we get to 6p. And then remember that after 6s, we go back and fill our 4f. And then we move on to 5d. And finally, 6p. We said that lead has to end with 2. And so let's see if this actually does add up to 82. We go 2, 4, 10, 12, 18, 20, 30, 36, 38, 48, 54, 56, 70, 80, 82. And there's our electron configuration for lead. It tells us exactly how many electrons are in each Bohr shell and each orbital within a lead atom. The one thing electron configurations don't give us, though, is any information about the spin of those electrons within those various orbitals. Orbital filling diagrams will do that for us. And so in an orbital filling diagram, just like an electron configuration, we follow the Aufbau principle, that our lower energy orbitals fill first. But now we're going to look at each of those individual orbitals and use Hund's rule, which tells us that degenerate orbitals, which are orbitals of the same energy, for instance 2p, 3d, something like that, are filled with electrons until the orbital is half filled before pairing up of electrons can occur. And we'll see what that means in just a minute. We also will apply the Pauli exclusion principle, which tells us that individual orbitals will have 2 electrons with different spins. And so this is the effect of Hund's rule here. Think about our 2p orbitals. We said that there are 3 p orbitals, and so each of these lines represents a single orbital within a p sublevel. If we have, for instance, some configuration that ends with 2p3, those 3 electrons are going to be placed singly in each of the p orbitals. By convention, we always write them spin up first. Then, if we do have more, so let's say it's a 2p6, now we would go through and place our spin down electrons into each of the orbitals, finally filling them up. And so let's take a look at nitrogen for an example. If we look at the electron configuration for nitrogen with its 7 electrons, it's 1s2, 2s2, 2p3. And so our 1s orbital is full, 1 electron spin up, 1 electron spin down. Our 2s orbital is full, 1 electron spin up, 1 electron spin down. Our 2p sublevel, on the other hand, with its 3 orbitals, each of those 3 orbitals have 1 electron that is spin up. We do not pair the electrons up until there is at least 1 electron in each of the 3 orbitals. And so here we just have several examples to look at. We have lithium, Its electron configuration is 1s2, 2s1. You might see orbital filling diagrams written in either way, either with simply all the orbitals laid out in a line, or sometimes you see them like this, with their relative energies increasing. Here we have beryllium, 1s2, 2s2, and so now we've filled our 2s orbital. And then getting larger and larger, boron, now with an electron in 2p1, carbon with 2p2, but again, you can see that we have one electron spin up in each of the 2p orbitals. Nitrogen, which we've already looked at 2p3. Then finally, when we get to oxygen, we will now begin putting spin down electrons in one of the 2p orbitals. As you may have noticed, when we get to larger and larger atoms, the electron configurations can get quite long. Look back at what we did for lead, for instance. That was a very long configuration. We can use what we call a noble gas configuration, which gives us a shorthand method of writing configurations. So let's take a look at a few examples. If we have the electron configuration of neon, we see it's 1s2, 2s2, 2p6. The electron configuration for sodium, 1s2, 2s2, 2p6, 3s1. Magnesium, 1s2, 2s2, 2p6, 3s2. Aluminum, 1s2, 2s2, 2p6, 3s2, 3p1. And silicone, 1s2, 2s2, 2p6, 3s2, 3p2. Now if we look at all of these, and I take a look at a periodic table alongside this, and you'll see that neon is the noble gas that comes before sodium, and then sodium, magnesium, aluminum, and silicone are all in the same period. If we take a look at these, though, we can see what the configurations have in common. They all have 1s2, 2s2, 2p6 in the beginning, which is the configuration for neon. And so what we can do is, instead of writing out 1s2, 2s2, 2p6, we can simply write neon in brackets. Writing that is the equivalent to writing 1s2, 2s2, 2p6. And so the noble gas shortcut for those four elements would look like this. Remember that this stands for writing out 1s2, 2s2, 2p6. I just write neon in brackets, and then the rest of the configuration after that, and so forth. And so when using the noble gas configuration, you can go back to the noble gas that comes before the element and write that in brackets, and then write out the rest of the configuration from there. For instance, when we were doing the configuration earlier for iron, if you look at a periodic table, you see the noble gas that comes before iron is argon, and so we can write argon in brackets. The rest of the configuration for iron from there is 4s2, 3d6. Similarly, the configuration for lead. The noble gas that comes before lead is xenon. The rest of the configuration after xenon would be 6s2, 4f14, 5d10, 6p2. Still fairly lengthy, but a lot shorter than what we had written before. This slide here gives several examples of lots of different electron configurations using the noble gas shortcut. I would encourage you to try several of these on your own and make sure that you can get the same exact answers. You'll take note here that chromium and copper don't seem to follow the same rules that we looked at before. We'll be taking a look at why those are exceptions in a little bit. We can also look at writing the electron configuration of ions. When you're looking at the electron configuration of an ion, first write the electron configuration of the neutral atom, and then remove electrons from the orbital with the highest principal quantum number. So let's take a look at a sodium ion. If we're looking at a sodium atom, our configuration is 1s2, 2s2, 2p6, 3s1. And so let's look at a sodium ion. From sodium's position on the periodic table, we know that sodium will have a 1 plus charge, which means we have to remove one electron. Our rules for the electron configuration of ions tells us that we remove an electron from the orbital with the highest principal quantum number, our highest value of n. Our configuration for a sodium atom shows us that the third n value is our highest principal quantum number. We have one electron in an s sublevel, and so that's the one that we want to remove. And so our electron configuration for a sodium ion is going to be 1s2, 2s2, 2p6. Let's take a look now at an iron ion. And so the electron configuration for iron is argon, noble gas notation, 4s2, 3d6. Now remember, when we're looking at the electron configuration of an ion, we want to remove electrons from the highest principal quantum number value. Even though our configuration ended with 3d6, 4 is actually our highest quantum number value. And so that's where our electrons will come from first. In the case of iron 2+, we need to remove 2 electrons. And so our configuration is going to be argon. Now we've removed the 4s2, and we're just left with 3d6. For iron 3+, we have to remove a total of 3 electrons. And so we're first going to remove those 2 from 4s, and then 1 from 3d, giving us 3d5. And there's our electron configuration for an iron 3+ ion. This can help us predict if something will be magnetic or not. Atoms or ions with unpaired electrons are what we call paramagnetic, and they will be attracted to a magnetic field. Atoms or ions without unpaired electrons are diamagnetic and not attracted to a magnetic field. And so if we have iron 3 oxide, the iron 3+ ions in there have 5 unpaired electrons, which makes that sample paramagnetic. Iron 3 oxide will be attracted to a magnet. And so let's take a look at why. When we're looking at an iron 3+ ion, we have no electrons in our 4s orbital. We have 5 electrons in our 3d. And remember that Hund's rule tells us that each of those electrons will go in first as unpaired into each orbital. And so in an iron 3+ ion, we have 5 unpaired electrons, making the ion paramagnetic, so it will be attracted to a magnetic field. Lastly, we have to talk about those anomalies that I mentioned earlier with chromium and copper. It turns out that if we can half fill an orbital, that has a more favorable energy state. And so if we look at the configurations of chromium, we would expect that to be argon 4s2, 3d4. And so the orbital filling diagram would then look something like this. It turns out, however, that if instead of this configuration, we actually take one of those electrons away from the s orbital and place it into a d orbital instead, then now we have half filled that d orbital. and that is a more favorable state than having it not half filled. And so our actual configuration for chromium is going to be 4s1, 3d5. Similarly for copper, our configuration we would expect to be argon 4s2, 3d9. And so we would expect those electrons to fill in something like this. And so similarly to chromium, though, it turns out that if we are able to rob one electron from that s orbital and instead place that into the d orbital, that full d orbital and a half full s orbital is a more favorable energy conformation. And so the actual configuration for copper ends up 4s1, 3d10. Now this is important because this leads to the reason why something like copper tends to quite often have a +1 charge, or silver right beneath it. Silver always has a +1 charge because it is very easy to simply remove that one 4s electron to form a +1 charge. And so in this video, we've looked at electron configurations and orbital filling diagrams in order to get an idea for exactly where electrons are located within individual atoms. I hope this has been helpful. If you are looking for more help, be sure to come see me, go to a past session, or go see a tutor at the Learning Commons.